And this is based on work with my very nice collaborators. So Jelle Harting in Edinburgh, his PhD student Vijay and Melly, and Gerben Oling, who's in the audience. So feel free to ask both me and him if you have anything that is unclear during the talk. Very good. So just to set the stage, well, wait, let's see. There we go. I had to press the other one. So all of this takes place within the context of, in some sense, flat space holography. And there is a very nice anecdote from Strings in '98, where Witten sort of muses on this topic. And he says this funny thing that, okay, we want to find flat space version of the ADS-CFT correspondence. But of course, the boundary in flat space, or asymptotically flat space, is a little bit funny. So he says this funny thing that, okay, a too naive version of structure X, which is this putative dual to gravity in asymptotically flat spacetime, is some kind of field theory on null infinity with what he calls the peculiar differential geometry. And as we will see, this peculiar differential geometry is precisely what has now come to be known as Carolian geometry. So just to give you a bit more motivation before we get into the meat of the talk, in the ADS-CFT correspondence, I don't need to tell you, of course, that the energy momentum tensor on the boundary plays a big role. It's sort of the response to varying the metric. And the way that you get this energy momentum tensor is essentially by performing this procedure known as holographic renormalization. And the way that works is essentially that you solve Einstein's equations near the boundary while keeping the metric on the boundary free. And then by varying the on-shell but renormalized action, because generically it diverges, so you need to renormalize it. By varying this renormalized on-shell action, you can extract, by varying this boundary metric, the energy momentum tensor on the boundary, which is then the CFT energy momentum tensor. So the goal of this talk will be to do the same for asymptotically flat spacetimes, namely carry out this holographic renormalization procedure. And rather than having a Lorentzian geometry on the boundary in asymptotically flat spacetimes, we have a conformal Carolian geometry. I'll tell you exactly what that means. So just by analogy, what we must understand is the near boundary on-shell description of gravity as captured by the Einstein-Hilbert action in asymptotically flat spacetimes, and in particular with arbitrary Carolian data at future null infinity. Very good. And please, if you have any questions, interrupt. Doesn't matter if I don't quite get to the end of the talk. Very good. So just to give you a small taste of what this word Carolian means, which we saw it already in Siki's talk, but in case you haven't really heard of this before, it's maybe slightly exotic. One way to think of it is as something you get when you take the speed of light c going to 0, in which case the light cones close up like this. And that has all kinds of peculiar consequences, namely that the screen goes black and there's no light in the Carolian world. Very everything. But just to make a long story short, what happens is that exactly the opposite to what would happen in the Galilean limit. So rather than time becoming absolute, which is perhaps more familiar, space becomes absolute when the light cone closes. And what replaces a metric in the geometric version of this is this so-called Carolian structure, consisting of what's called the Carolian vector field and a Carolian ruler, which has co-rank 1 with a kernel spanned by this Carolian vector field. And you should think of this H as sort of like a spatial metric in quotation. It's not a metric, but it sort of measures spatial distances. In the context of what we're doing here, you should maybe think of it as some kind of generalized version of the metric on the celestial sphere. If we add sort of conformality to the mix, these structures and their inverses, so tau and h, it's not too important, but together with the v and the h with the indices downstairs, these form a complete set of sort of what corresponds to the metric and its inverse. And they transform in a certain way under Weil rescalings and under these so-called Carroll boosts, which is sort of, yeah, they shift this so-called clock form, which is the dual to the Carolian vector field, and there's a v missing here, so this should be 2v mu. So these symmetries will come back to haunt us later. But just to tell you what exactly I will be talking about. So first, I'll just discuss how you actually get this near boundary structure up and running, and how to really see this completely arbitrary Carolean geometry on the boundary, namely on null infinity. Then I'll tell you about how variations work in this framework. It'll turn out there is a certain constraint that the formalism places on the boundary geometry. So you need to deal with constraint variations. And then at the end, I will go through the procedure of holographic renormalization for asymptotically flat spacetimes. And in particular, that will reveal that the shear plays a very important role. So to set up this framework, what we're doing is really just, we consider a box standard Lorentzian metric in an asymptotically flat spacetimes, and we write it in a vielbein decomposition. So this is, this is a very standard thing, except that here, rather than having sort of normal time-like and space-like vielbein, we've combined one time-like and one space-like vielbein into two null vielbein. So this you can always do. And then we treat null infinity, so the boundary here, as a Penrose boundary, and there is a very standard thing that Penrose came up with, which essentially involves the introduction of what's called a defining function, which is basically the radial coordinate that is such that when you take it to infinity, you land on null infinity. And what you do next is you just partially gauge fix the local Lorentz transformation that acts on these vielbeine to get the metric into this form. So these objects will appear quite frequently, but this is just a choice of your local Lorentz transformation. So we don't fix all of it, but we fix them such that we land on this choice. And then this Penrose construction fixes the boundary conditions for the fields that appear in these objects. And precisely what happens, and we will see exactly how this goes, what exactly happens is that when we go to the boundary, these objects essentially give rise to this Carolean structure that I showed you on the previous slide. Of course, they appear at different order in R. So, for example, this the thing that gives rise to this so-called ruler appears at order R squared, and the expansion of this pi, which sits here. But this is all dictated by this Penrose construction. So we've already fixed some of the local Lorentz symmetries, but there's much more to fix. We have a lot of fixing to do. But the strategy is really to fix all symmetries that we can, such that the boundary Carolean structure remains completely arbitrary. And this is important precisely because we want to vary it so as to get a response, just like in the ADS-CFT correspondence. Normally, so in order to do that, we fix these Levi-Civita connection components here in this way. And in some sense, this provides a covariant generalization of the Bondi gauge. So that's why we call it, and it's covariant with respect to the Carolean structure. So it's Carroll covariant. Of course, what's usually done is that you fix the symmetries further to go to the full Bondi gauge, where the clock form is related to the retarded time. And this metric, the ruler here, just reduces to that on the celestial sphere. Where I remind you that D, again, is this, essentially, so D plus 2 is the dimension of the bulk space-time, so D plus 1 is the boundary, and then, of course, the celestial sphere will have D dimensions. Now, as I mentioned, there is a constraint, and this constraint enters here, so it turns out that Einstein's equations force this so-called, it's related to something called the intrinsic torsion, but this funny extrinsic curvature looking thing, K mu nu, which is the lead derivative along the ruler, along the Carolean vector field of the ruler, is constrained to be pure trace. So this is a constraint only when D is greater than 2. So in particular, it is a constraint for full bulk space-time dimensions. But we'll see how to deal with that later. Now, if we solve Einstein's equations order by order in R, what we find is the following. So the expansion looks like this. So at leading order, we already knew from the Penrose construction, we get the Carolean ruler. At the next to leading order, we get this C, which is the shear. So it's symmetric and trace-free and spatial, which means that if we contract it with V, the Carolean vector field, we get 0. This S is quite important. So remember, S was really the GRR up. So it's going to be related to the norm of the normal of a constant R hypersurface. So that's going to be important when we consider holographic renormalization and cut off constant R hypersurfaces. but we'll get there. The last thing on this slide is just an explicit identification of the residual transformations with the Carolian symmetries I showed you on the first slide. So the residual diffeomorphisms look like this, where in particular the radial component of these guys become the Weil transformations I showed you on the previous slide. The subleading boundary diffeos become Carol boosts, parameterized by this lambda. And then these leading guys just become boundary diffeos, the parameter of boundary diffeos. And so these two we already saw, but this guy, the shear, which of course is a very important object because it sort of, if you were considering scattering problems, that is sort of the thing that captures graviton scattering. But here it's just a funny object that transforms in a certain way. So it has a derivative on the boost parameter, suggesting a connection with, some kind of Carol boost connection. I will not go into it. I will just mention that this covariant derivative is a particular choice of covariant derivative for the Carolian geometry. The details are not so important. You can make any choice you like in a sense, as long as the full thing behaves nicely. So you can endow this with certain properties, but ask me later if you're interested in how that works. Very good. So if you then, in a bit more detail, solve this thing, what you find is that the metric, the near boundary expansion on shell looks like this, where you see the shear sitting in this component. And then you see in this component that you have, well, here I have abbreviated things a little bit, but these guys are all essentially defined in terms of geometric data that comes from things like, curvatures and things defined in terms of tau and h. But there is some structure that is not determined by Einstein's equations, and that precisely will go into the definition of the energy momentum tensor, and we will see how that happens. So just to give you a little bit of an idea of how these variations work, if you take an action functional depending on the Carolian structure and the shear, its variation looks like this. So it will turn out that the shear is on par with the Carolian structure, so that the variation takes this form. And together, these three responses define what's called an energy momentum tensor news complex. So the energy momentum tensor plus the news. And by varying these guys under the symmetries of this action, so which we assume are there, they turn out to not be quite there. But if we assume they are there, we get certain void identities corresponding to diffeomorphisms, Weil rescalings, and Carol boosts. So they will come back to haunt us as well. But now, for the holographic normalization, what you need is essentially a well-posed variational principle. So if you just take the Einstein-Hilbert action and you vary it, you find that it's a boundary term, so there's an x missing here. But it takes this form in 4 bulk space-time dimensions. And the standard thing is that you need some kind of Gibbons-Hogg-Yawking boundary term to make the variational principle well posed. But here, this S guy that I mentioned comes back to bite us, because if you do this on a constant R hypersurface, you find that this hypersurface doesn't have a definite signature. So it's not null, it's not space-like, it can be anything. Luckily, roughly 10 years ago, these gentlemen came up with a counter term that precisely deals with this issue, and it takes this form. And when we then add this, the variation takes this particular form. This part we like, it looks like what we had in the other slide, but this part we don't like because this precisely contains variations of free data. So we cancel that by just adding this term that removes this variation. And this, in the context of ADS-CFT, would be like a cosmological constant term. But so that we add, but that introduces additional divergences that we then must get rid of. And it turns out that we can get rid of these by adding this term, where C is now some well-chosen connection on these constant R hypersurfaces. In addition to that, we can introduce improvements via finite counter terms that endow these responses with certain properties that we like. So once we do that, add a suitable intrinsic counter term, which is reasonably complicated, but it can be done. It looks annoying, so I don't write it. But once you do it, you find that the full variation, as you go to the boundary, takes this form. And what is a little bit special, and what you should really appreciate here, is that this funny term here appears. So you see, it's not here a priori, but it really appears for two reasons. So this curly t, which is sort of the finite version of the t, is order r to the -3, plus the fact that if you take s with delta h, that is a total derivative. And these two facts combined give rise to this structure and really is what pushes up the shear to be on par with the Carolian structure. So that is something quite special that happens as a consequence of this holographic renormalization procedure. And then you can see, okay, suppose that this action was actually invariant under all the symmetries. We'd have these void identities that I showed you on the previous slide. And then you just say, okay, you can explicitly compute these guys from this procedure. Do they satisfy these void identities? And it turns out that they satisfy the Weil void identity, but not the boost void identity. There is a boost anomaly. So this anomaly is Wess-Zumino consistent, and it just sits here. So the boosts are anomalous. Very good. So the diffie void identity turns into a covariant version of the Bondi loss equations. They look like this. I'm just flashing it here to say that there's an explicit result that reduces to known results when you sort of gauge fix further. And this n, in case you're wondering, is sort of a Weil invariant version of the News tensor. So usually the News is just the retarded time derivative of the shear. And this is, if you take v to be like minus du, this is roughly that, and k to be 0. So to end, let me just give you, so of course this opens up many, many interesting new directions of future research. So one burning question is, of course, does there exist some kind of analog of n=4 super Yang mills on the boundary that we can somehow write down? Is there really a dual field theory that does this? Is there some kind of Carolian boundary CFT? We don't quite know, I would say. Of course, since we're at Eurostrings, it would be extremely interesting to connect this with other very interesting works that actually explicitly embed a simplified version of this into sort of topological B models, where you can consider a stack of D1 branes and get a very interesting version of this for something called Bern space. So that would be interesting to see if there's some connection with this. And then more generally, just to connect this to this whole celestial program, where instead of considering the dual to live on this null infinity, you really consider the dual field theory to live on the celestial sphere over which null infinity fibers. So yeah, thanks a lot for your attention.
Questions? Yeah.
Regarding the Carroll boost invariance, so in your boundary action, you were varying the field that you call ruler, so H with lower indices,
yes,
but also the clock one form and not the vector field.
Yes.
Can you comment why you used clock one form and not the vector field?
Yeah, so the thing about that is, so that is a choice. You could also vary it's just because the way that the energy momentum tensor is, so the response to varying the clock is the energy current, and that's sort of more convenient to vary with respect to than, so you could have also used the Carolian vector field, that would be equivalent.
But the clock one form is not Carroll boost invariant.
No, exactly. And what that means is just that you get the boost void identity will involve the energy current, right? So you write T mu delta tau mu, and then you transform the tau mu under a boost, and that then will tell you if you were in a pure Carolian theory that the spatial projection of the energy current is 0.
Okay.
Great. Thanks a lot for the question.